Right, well, this is lecture 2, and we're going to talk here about eco-minimalism, which is where we look at how buildings have been evolving through the ecological design process over the last 30 years, and some lessons we've learned and how we might apply these. So if we start back in '69 with Man on the Moon and the great future that was foreseen for space travel, and this was the future, and all the space people were in the big offices, and somewhere down in the basement was somebody doing wind turbines, and the future of the world was definitely in outer space rather than on inner space. And this is actually the Gedser mill, which is one of the first major grid-connected mills at the south end of Denmark. And here we are in 2012, and what has actually happened is no men on the moon and millions of wind turbines. So the future's turned out somewhat different from the way it was foreseen in the days of Dan Dare and the Eagle and comics of the 60s. And we are in fact in a much more earthed world as opposed to a space-borne world. In those days, we were, as I explained in my previous session, we were actually zooming out to do stuff. We had this global perception of the world in crisis, and we were going out and we were making these. These are all solar collectors and bits of kit that my students and I were making in Hull in the 70s. And we were even using goat shit in order to try and make methane. And if you see in this tub on the right is goat shit, and the gas coming off is going and being bubbled underneath into another bottle. And just to prove that methane comes off, then there we are, we've burnt it. Isn't that wonderful? Except for one little problem. Spot the dilemma. In order to keep the goat shit at the right temperature in order to generate methane, we had to put it next to a gas fire. So unless you actually want to engage in shoveling loads of goat shit, it's really an exercise in redundancy. A skinny version of me there down on the bottom left, putting a wind turbine on the roof of our office in Hull, which actually generated just about enough to boil a kettle. An awful lot of effort for very little return, and that is one of the problems of micro turbines. But we built them. We built ones that were Cretan mills. We even had a project with a 250 kilowatt mill for a housing project in Hull, and then the crazy stuff like the sawn off oil barrel that generates all of 10 watts. The architect's favourite, the vertical axis windmill, because it looks sexy but actually doesn't work very well. So we were through the 70s doing lots of these things with all the pioneers of the industry at the time. Now, wind forward a little bit. In the middle of all that, we were approached by Granada Television to get involved in a program for refurbishing an old barn into an eco house. The architect was actually from Manchester, and we were there as what you might call academic support, talking through how we might get involved. And what we found was what you can see, which is the solar thermal roof, the wind turbine, actually not quite complete there, the greenhouse with its rock store underneath, and the heat pump. All those things you could see, and the garden, which was supposed to be a productive entity as well, all actually performed poorly. We went back to this project a year later and discovered that, in fact, the things that were working well were the things that you couldn't see: the high insulation, the draft-proof layer, and the kitchen heat recovery. So low-embodied materials also made a good score. And basically, we learned then in '76 that what you can see doesn't always perform well, and what you can't see very often does. And therein lies the trick, is that if you want your green badges to show, you may actually not be successful. And if you want them to be subtle, they may well be a lot more successful than you'd anticipated. And what is amazing to me is that people don't actually crunch the numbers. And I'm going to show you a project here where somebody did crunch the numbers for a project in England. a guy called Peter Worm, who actually looked at a single project and looked at all the options from, on the left-hand side, getting the heat loss down to a silver standard, a gold standard, looking at low energy light fittings and so on, up to the far end where he was looking at micro turbines and then through to larger scale stuff. And what we have here is a capital cost, which are the blue lines. In other words, this is the cost of any intervention that's being proposed for this house in terms of the pounds per tonne of CO2 that are going to be saved. That's the investment cost to save money and carbon. And then the revenue benefit that's going to come from having spent that money. So if you look at the very right-hand side, what we have is a 400-watt micro turbine, which has a huge investment cost in terms of the tons of CO2 that are going to be saved. And what we have is an output which is tiny. And if we look at the equivalent of doing the opposite, which is putting the turbine where the wind is, which is on top of a windy hill, what we will get back is 20 times as much. Now that's perfectly obvious to anybody who thinks about it. We tend to place houses where there isn't any wind because we want to be in a sheltered place. So it's pretty obvious that if you're going to put a turbine on top of something that's in a sheltered place, it isn't going to perform very well, and indeed that is what has happened. On the basis of crunching the numbers, on the basis of actually calculating everything, what happened with this project is as follows. Certain things just dropped out of altogether as being unviable, and others came on as being very viable. So finally, through proper calculation, it was possible to actually decide what to go for. Now, those who cannot learn from history are doomed to repeat it. So there we are in 67, and 40 years later, along comes a company called Stuart Milne, and they decide they're going to make a house that has small turbines on the roof, thermal collectors on the roof, photovoltaic collectors on the roof. Basically, they were going to spend an extra £21,000 so that they could actually put all this kit on the roof. Well, the payback period for that is about 100 years. The life expectancy of the technology is about 20 years. So I don't know what you think about that, but my view is that's not a very good investment. Interestingly, because in the UK it's turned out that 90% of people who put on conservatories also put heating in our conservatories, then if you add on a £20,000 for a heated conservatory, you'll never, ever, ever get your money back. And so my version of this is Plan B, where we wipe all that off, we just take it all away, and instead we actually add extra insulation and we make sure it's draft-proof and airtight. And that costs £8,000. You get your money back in 5 years, and the life expectancy is 50 years. So a factor of 9 difference in terms of the cost effectiveness of the intervention. Now, I was told by the quantity surveyor who was involved in pricing this project to blame it on the Merton rule. The Merton rule is Merton Borough in London has decided in its wisdom that all projects should generate 10% of their on-site. Now, the on-site is the key word, 10% on-site renewables, which means that we have wind turbines in the middle of London that are working off the exhaust from the air conditioning from the buildings next door rather than from the wind. Pretty disgusting, pretty stupid, and yet we're doing it. Now, this particular house was built, there you see it actually built as opposed to the drawings. It was monitored, and what they discovered was the energy use was twice what was predicted at Passive House Standard. The photovoltaic panels gave off only 74 watt-hours a day and was substantially overshadowed, you can hardly believe this, by a new neighbouring building. Now, given that this was built in the grounds of the Building Research Establishment and they had a choice of whether to put a building next door to it or not, that's a pretty astonishing decision to make. The thermal solar panels were difficult to regulate, and then they were made obsolete by the manufacturer, so they were US. And the micro turbines not only underperformed with very little output, but one fell off the roof. Again, not an unusual circumstance. The occupants found the ventilation controls too complicated. Now, that is also extremely common, that the systems that are thought up by mechanical engineers are far too difficult to actually be simple to use. And opening and shutting a window is one of the easiest things to do, but they don't seem to be able to bring themselves to make technology at that level. So there we are. It's just become so silly, and yet we've waited 40 years to get back to a point where both of these projects are actually deciding that what we were doing in our practice 30 years ago makes sense. This was the UK House of the Year in 1991, and I call it the birth of eco-minimalism, because the whole house basically worked off what was then a 5 kilowatt wood stove. And here we are 20 years later, still with minimal technology and no heating. This is a house we happened to get the House of the Year this year for the first passive active house in the UK. That means we designed it with a passive house certificate, but it can convert into an active house by simply opening windows and turning off the mechanical ventilation. And this is our award for architectural excellence for this little latest venture into zero impact design. This is a book that I produced 4 years ago. I've just been asked to do the second edition. And the thesis I will try and outline as quickly as I can. It's very straightforward. And I'm going to do it in the form of the 4 elements: earth, air, fire and water. I'm going to take you through, first of all, the things that I think don't work, and then counter those with something I think is a better strategy. So on the left-hand side, you will see well, first of all, I'll go through the 2 scenarios. If we look at earth, air, fire and water, and we look at the technical approach to sustainable building, I can guarantee you that this approach will make the green add-ons cost 15 to 50% more for any project. If, on the other hand, you take eco-minimalism, a good housekeeping approach to sustainable building through earth, air, fire and water, you will find that you can build it in to make it green at no extra cost. And I know this from projects I've actually worked on where there has been no additional cost for the eco-interventions. So on the left we have eco-bling, and on the right we have eco-minimalism. And let's start with number 1, which is the fire. If we have photovoltaic cells, we find we can only get a 50-year payback period, and given that the degradation in these is 1% per annum, this is really fighting very hard to try and win back some energy points. On the other hand, we can save 10% of energy simply by having reducing the impact on the national grid. In the UK, 10% of energy is lost simply by having the standby buttons on televisions and other machinery, and we now have already the technology to go back to a 1 watt standby or even a 0 standby, and we haven't been using this. Now if we look at the possibilities of solar thermal, then as against passive solar thermal, the problem here is not that it doesn't work, because it does work, and even a very simple solar collector can be made to work fairly efficiently, quite a cheap self-build. But in fact, the problem is that they tend not to be robust, and they tend to fall apart after about 10 years and then become redundant, and that means that effectively they have not paid back over their payback period. Passive solar, on the other hand, can be very effective. On the other hand, as you'll see later, it can also be a risk. Heat pumps, very common. People say they'll get 4 to 1 for every bit of energy put in, they'll get 4 out. But in fact, having put 3 of these on buildings in my career, I know that you're lucky to get between 2 and 2 to 1, and that doesn't get anywhere near the difference between the tariff of using gas and electricity. So you're really, again, fighting. If you're going to have passive, then you do need to have solar shading, because that prevents you having to put in air conditioning. So see it off at the pass, don't wait for it to happen. On the left here we've got a combined heat and power unit, which means that not only are we generating power, but we're also getting hot water from it. And this is great if you have a known summer load, but otherwise you've got a misbalance between winter and summer. Energy efficient light bulbs are an intervention that is so easy to make savings, and yet we tend not to think about it. It's just too easy. Condensing boilers were thought to be a great idea, except for the fact if you buy a cheap one, it doesn't condense and it doesn't work. We only recently have had, but are now worth seriously thinking about, very small boilers with a very good turn-down ratio. If we look at district heating and density and use, district heating works fine if you have the density of use and you have the right usage patterns, but it's not a catch-all. And as always, the best solution for everything is to go to super insulation and to make sure that you don't actually need a supply side. You've already seen it off by reducing the demand. It's so easy, and yet it's so rarely done. I've already mentioned the fact that if you have a conservatory, 90% of these get heating systems put in them. So although it's supposed to be free solar energy, in fact, it works in reverse. A much easier strategy for any building, rather than thinking about trying to get free heat from the sun, is actually to stop the heat leaking by drafts. And therefore all buildings should be airtightness tested. Now again, I'm talking about Northern Europe because that is where it is very important to stop the cold weather and the cold winds from going through the house. I'm showing again this is a 1977 project, and it was an awful lot of effort to try and make a wind turbine produce heat, and in fact it really didn't work out. If you're going to really take wind seriously, that needs to be in wind farms and in intensity. And engineers can take us to enormous lengths. This actually, believe it or not, is a BREEAM excellent building, and yet it's covered in exhaust systems and fans, and I really don't understand how that can be necessary when, in fact, we can do it in other ways. We can deal with moisture and toxicity in this building called the Breathe building. I'll show in the case studies later. Now, in terms of water, you can go to all sorts of lengths in order to try and make water clear. On the left is a living machine. It's at Findhorn in Scotland. But on the right is a simple conservation toilet, which just uses 1/3 of the water of a normal toilet. And these systems can often be much easier and more readily used than the complex treatment once you get it down the end of the pipe. It doesn't make sense to go for a reed bed sewage system in an urban area. On the left, you'll find it's land hungry. It's 3 square meters for each person that uses it. On the other hand, you can deal with water very effectively by having land that is easily drainable. So also considering water, on the brick building there, it's quite interesting. They tried to recycle grey water, but found that pollution was getting in because people misbehave in the bath and the shower, and therefore a very good idea to try and get the heat and reuse the water was actually undermined by the way in which people use things. I keep saying that sociology will nearly always beat technology, because people, if something can go wrong, then it will go wrong. It's very unusual for people to think about pipe-free water wastage systems. And if you look at the waterscape strategies being used by Mr. Dreiseitl and friends, it's very exciting that we could actually take something we tend to put under the ground and hide away and make it very exciting. And materials, how not to build. Don't build with recycled materials, but do build for materials that can be recycled. On the left we have a motorway that's taking longer to demolish than to build, and on the right we have a nail-free construction that can be taken apart without wrecking the timber. So it's 2 ways of looking at something. Quite often trying to use recycled materials is a very, very intensive activity, and you're just better off not going there. I have a problem personally with turf roofs and sedum roofs. I think they're an eco-camouflage, because very often underneath them is a plastic roof. And if we're going to be looking at developing soft landscaping, then I think we should be looking at edible landscapes. This on the right is a car park that has apple trees growing between the parking bays. And we can look at all opportunities for actually making different species and productive species part of the urban infrastructure. On the left is a building that's made out of rammed earth. It happens to be in an area where you get it very readily because it's in south of France and in the Grenoble area. In terms of Scotland, what we're looking at more and more is what we have, which is timber, and mass timber in particular, because it has a terrific ability to mop up carbon. It's a carbon sequestrator. So these are the options when we're looking at two ways of looking at buildings. One is we can go technology hungry, and the other we can go to passive interventions. So be careful of Mr. Eco-Bling, who's going to try and sell you the snake oil remedies, and look to doing it simpler. I'm going to do a Tale of Two Cities here, which is a project I think has set back the green agenda by an awful lot of time. And it's an inner city project in London, which has tried to tick all the eco boxes of 30 years ago. And actually what's happened is that it's cost a lot of money. Its residents are basically greenies, and it's expressing its technology in a way that a lot of people find not terribly user-friendly. And I think the message is this is given out, this is the BedZ project in London, is that it costs more to build green, it's only for greenies, and it looks different. And after 5 years of hearing hype and all the sales pitch, the architect has finally said and come out and said, next time no moving parts. And we've been waiting to say this for some time. But however, it's had a lot of publicity. In the meantime, other projects, such as the one that I've showed you before in Perth, it has also its own agenda with healthy materials, natural ventilation, super insulation, air tightness, and so on and so forth. And it was built at benchmark costs. Very importantly, it was built at the same cost as a non-green project. Its residents are ordinary social tenants, and they shouldn't have to be greenies in order to be able to live in this project. And its differences are virtually unseen. So the message it gives out is that it can cost the same to build green, healthy buildings are for everyone, and it doesn't have to look different. And that's my eco-minimalist message. In other words, healthy buildings don't have to cost more than toxic ones. Now, I have been costing a lot of our buildings over time, and that particular one we built for £780 per square metre, which is the equivalent for housing in communities across Scotland. I first learned my lessons in what to do and what not to do when I was bounced into a lot of technical systems where the mechanical electrical services represented 30% plus of the cost of this project that I did in a recreation centre in Scotland. And I realised that actually conventional M&E specification, mechanical electrical specification, tends to be very overhyped. Everything's a factor of 2 more than it needs to be. And when I did a project 2 years later, actually 4 years later, where I had control, I actually did my own mechanical electrical, and I designed it a bit like a housing project where I don't employ a mechanical engineer. I found that all the savings that I could have made on this first building, we were able to translate and more into the one where we had our own control. We modelled it, and we knew that we could actually get these amounts down. And we ended up with something that was only 9% of mechanical electrical service instead of 30%. Now what that does is that extra yellow wedge, you can spend all that money on good quality fabric. You don't actually have to spend it on technology, which is the bit that goes wrong anyway. And I'm going to give you a short illustration that you will know from your own intuitive use of, let's say, something as simple as washing your hands in the toilet. Here we have a choice of a paper towel dispenser and a hot air blower. Now, the paper towel dispenser is quick, low energy and clean. The hot air dispenser is slow, 9 kilowatt hours, 9 kilowatts of energy. It's in fact 250 times more unhygienic than paper towels. And that means hygroscopic materials are 9 times more effective than mechanical ventilation at dealing with moisture. Architects' cheap green option on the left and an engineer's expensive option on the right. And I'll show you 2 buildings that actually show you that green specifications can cost less to install and less to run. On the left we have the Breathe building I talked about earlier, And on the right we have the building where the engineer decided that it was all going to be run with lots of technology. And in this, the Adnams Brewery building in the East Anglian area of the UK, what they did was they used materials that were highly hygroscopic, and in fact it was limecrete. It was a mixture of lime and hemp. And they relied on the building materials to cope with the moisture levels in this brewery store. The engineers had put in mechanical ventilation, which was actually £400,000 in cost. And the client says, well, if this system's going to work, it's going to work. Let's just take all that out. And they did. They value engineered out the M&E. And in fact, it's been working now for 5 years perfectly well with no technology. So it can be done. You just have to know that it can be done. And these are case studies in Germany where, in fact, only 1% extra for design and environmental modelling delivered 25% capital cost reduction and 50% energy savings. These are the solar power projects in Germany. To put that into a context in where your bung for your buck is, let's have a look at how we spend money on buildings. Capital costs need not be more for green buildings, but what about the running costs? Because if you're actually owning a building and running it, what does it cost to run? Well, the construction costs, let's say the construction costs are 1 unit. The building operating costs for the building that's being constructed are 5 units, and the user's salaries are 200 units. So that means that really the construction costs are almost irrelevant by comparison with when the life of the building is in use. It's about the user's salaries. Now, think about this, because if you have built a building where people don't like it, and they don't like it enough that they actually become absentees from their work for a period during the year, then that's going to cost you. So if you get a designer in, and remember a designer is only 0.1% of the construction cost, then we're actually saying that you get a designer in who doesn't understand about indoor climate, you could have an impact on your users' salaries that's very significant. For example, if there's a 5% improvement in attendance, i.e. non-absenteeism, it's 4 times the operational costs and 20 times the construction costs during the period of that building's use. All for the sake of spending an extra 0.1% in designing and modelling the indoor air quality in the first instance. And this is the sort of nonsense we get where everybody's paying peanuts and they're getting monkeys and they're getting monkey buildings. And in order to elaborate on this, I'm going to show you 4 of our buildings where we have applied these principles and we have been successful in delivering buildings that are fit for purpose, cheap to run, and are sustainable. The Glencoe Visitor Centre, which we built in 2002 and won an international award for, was replacing an old campsite and an old visitor centre. And we did it on the basis of the different elements of the building, like the skins of an onion. And we used different timescales so that we looked at the relevant costs. For example, if you look at the graph on the top left, you'll see that the structure will last for 50 years, the services on average for 15 to 20, and the space planning for only 5 to 7. And when you add that up over a period of 60 years, you see that the structure is a very small part of it. The space planning, the services end up being a very expensive part of it. So if you build a passive building, you don't actually have to spend on the yellow and the red bits over the 60 years. Get that bit right, and you're saving a huge amount of money. We built this so that we could actually lift the floors and replace them by using a nail-free construction. And you can see the plumbing and the electricity going under the floor there, and those boards can all be lifted free. We took a long time to make sure that the infrastructure for the plumbing was as efficient as possible and reduced the treatment plant by 1/4. We had low impact foundations so that there was a light footprint on the ground and not lots of concrete. And we were also looking at the operational efficiency as against actually the generating. As it happens, we were using wood chip for the heating system here It wasn't a totally passive building, but it was extremely efficient. And we sourced all the timber locally. It was completely untreated, and about half of it was from independent suppliers. And it was a combination of what you might call Scandinavian and Scottish traditional architecture in juxtaposition with each other. Here's some of the flooring. You see the detailing there. And it's a mixture of timbers, from beech to birch to oak to sycamore. That was probably at the time the lowest impact building that we had ever done, and stands up to scrutiny throughout Scotland. This is a project we did with Rotherham Council, and we were the advisors for the ventilation system, and in fact the lack of a ventilation system, because we used hygroscopic materials. We did all our specifications for them, and the building was built for people with breathing difficulties. It was for miners and steel workers who had pneumoconiosis and various other diseases, so it had to be right. And we modelled it, and we managed to deliver natural ventilation using thermal mass as well as moisture mass, and we had an underground labyrinth to preheat the air in spring and autumn to cool it in summer, so we didn't need an air conditioning system. The air is extracted at higher level windows with fan assisted at high external temperatures. In winter, the ventilation enters at the atrium roof level in a mixed mode. So we had a hybrid system here. We carefully selected the materials, and I was the advisor for that. The vapor permeable external walls controlled the humidity, and the thermal mass was used for energy efficiency. So it was a passive building, and it's worked incredibly well. Its cost was about £2,000 per square metre. Finally, or nearly finally, I'm going to present the Carrickle Primary School, which is a building we completed 3 years ago, and which, again, we pretty well did every trick in the book on this project. We used mass timber. It's the first mass timber building in Britain to sequestrate carbon. It's a passive house guarantee. We had humidity control through both this and the clay plaster that we used in the classrooms. The paints were vegetable paints, so that any moisture going through the walls, it was open porous, and all of these dealt with the humidity and the low algae requirements. We also commissioned specially healthy furniture, because surprisingly there is no furniture made for schools in the UK that actually has healthy finishes. So we actually had this specially commissioned with special paints and low allergy off-gassing, and it was unique to this project, and we're very much supporting this manufacturer in the future. So basically, on the basis that hygroscopic materials are 9 times more effective than mechanical ventilation, we were able to remove the mechanical ventilation, normally a prerequisite for a passive house building. The open porous paint allowed the moisture to permeate. It was vetted for low emission environmental properties with the furniture, and the structure of the building sequestered 1 million kilos of CO2 and cost us a mere 50,000 kilos to get there from Austria. So basically we're on a winner here. The indoor air quality, we went through all sorts of different ways of looking to ventilate it, and all these options were modelled and reviewed. We even had a culvert system at one point, but decided to keep it simple eventually, with just simply openable windows that worked off the temperature and the carbon dioxide levels. So we eventually went for this natural ventilation system, and the following is being used: temperature, humidity and CO2 feedback, remote Velux operation for the window master, lobby door cranking in summer. And in the nursery school, we've made sure that all the window heights suit the children, furniture is non-toxic, and the nursery is again done in a child-friendly manner. So, in summary, the modelling of this project has delivered a passive standard, a 4.5% daylight factor, which prevents them from having to put artificial lighting on during the day, a 12 times energy reduction above building regulations, and we got the mechanical electrical costs down to 13% by cost, as opposed to what would normally be 30%, because we did all the modelling up front and worked with the engineers up front to make sure that we didn't have to over-specify the mechanical ventilation. We have post-occupancy benchmarking, which means that we can check that this building is doing what we said it would do, and over 3 years now we've monitored it, and it is performing as we wanted. Within each classroom are feedback mechanisms that the children and teachers can read all the time, which gives the temperature in the classroom, the relative humidity in the classroom, the parts per million of CO2, and the lighting levels. So they get real-time feedback on what's happening in the classroom, and they know whether they're comfortable or not by the dials on the wall as well as their subjective feelings. Within this, we have deliberately exposed the surfaces in the corridor so the children can see how things are getting about the building. We have different colours for each of the classrooms so that they can feel that they've got their own space with their own colour scheme. And the classroom corridor, which is on a slope, allows for outside library use outside each room. Again, that was agreed with the client. The colouring, you'll see here, we have what's called a lasure technique, which is a light brushing of natural vegetable paints. And the colour scheme was done by a specialist colour advisor. And each of these colours is related to psychological reactions to colour. So, basically, the summary of this project is that we've had low emission materials and hygroscopic materials to give a good, healthy indoor climate. We've got a significant ventilation reduction, good acoustics, a site-wide water strategy. We've got some off-site renewables in order to be able to deal with the hot water loads because everybody has to wash their hands, a professional colour scheme, new zero emission furniture, and 1 million kilograms of carbon sequestration. So we feel this is a significant step forward in a holistic approach to eco-building. And we managed eventually also to get external post-occupancy evaluation funding, which means that we can prove that what we set out to do has been done. A very important thing. And I'm really just showing our latest project here for no reason other than we've won some prizes with it. We think it's rather nice, and it happens to be our latest project. So it's, again, an essay in wooden glass and eco-building. And with that, I'm going to finish my talk and hope that you've enjoyed the 2 sessions we've just done. And these are the contact points. If you want to see others of my lectures, you can go to gaiatv.org. And if you want to get to all of our material for publications, then you go to www.gaiagroup.org. But I will actually be giving Chris some versions of this lecture on PDF, and you can have those for reference. So again, that's the end of talk 2, and I would now like to go into question and answer routine, and look forward to talking to you.